Okay, morning everyone. Welcome to semester. We are experimenting with both broadcasting on Zoom and doing it in person as well. So if you're on the so our first speaker is you have to excuse me for poor pronunciation, but Tathagata.
Yeah, that's right.
And he's going to tell us about the stochastic path integral analysis of the
Continuously
mounted simple harmonic oscillator. So over to you.
Thanks to Professor Lisa for the introduction. Yeah, I'm Tathagata. I work with Professor Jordan, and this seminar is on Jordan. Could you excuse me for a minute? I think I'm hearing echoes from myself.
Okay, I'm going to turn the volume down here.
I think that might be another issue. That's fine.
Good.
So this is on stochastic path integral analysis of continuously monitored simple harmonic. As the title suggests, slow.
Yeah.
So, as the title suggests, we provide a stochastic path integral formulation for a continuously monitored quantum system. The Chantasri-Dressel-Jordan formalism, and it has been applied to qubits before. And in this work, we extend it for the first time to continue. We extend it to quantum simple harmonic oscillators in general Gaussian states undergoing simultaneous, weak, continuous position and momentum measurements. The top, I'll first talk about measurements. I'll introduce something called the POVM, or positive operator value measured, and weak and weak continuous measurement. And then I'll discuss how where Chantasri-Dressel-Jordan stochastic path integral formulation comes into play. And then I'll go on to describe our system under consideration. And as I already have mentioned, that we assume that the system is in Gaussian states. So I'll define what I mean by Gaussian states and what are the relevant parameters associated with them. And I'll describe how the state of the system evolves under continuous measurements. And then I'll talk about what this Chantasri-Dressel-Jordan formalism tells us for our particular system. And next I'll go on to discuss something called the optimal paths, which comes from the Chantasri-Dressel-Jordan formalism. And then I'll conclude. So let's begin. So we know from introductory quantum mechanics that the von Neumann measurement schemes that any observable A can be expressed in terms of its eigenvalues and projectors to its eigenvectors. And when you measure the operator observable A, then you get the outcome lambda n with probability given by this trace pi n rho pi n. And again, you can update the state of the system. Excuse me. Yeah, you update the state of the system according to this rule. And basically, after the measurement, you will project the state to the eigenstate of this A observable corresponding to eigenvalue lambda n.
These projections are not complete.
Sorry?
This is partial projection.
No, these are complete sum assuming, right? And
You start with pure state?
not necessarily in density matrix, but I assume there's no degeneracy. I assume that for simplicity, there's no degeneracy or anything.
They're
There's no-
one-dimensional projectors.
So why is it density matrix?
Well, the
You say
initial
state
state.
and you say density matrix. I like states, pure state. I don't like density matrix.
I mean, I'll be discussing with density matrices. So what I'll be discussing next will come in terms of density matrices, because we,
System described by density matrix is pure state. Only system entangled with something described by density matrix. If you have system which is
Okay, he's using density matrices. That's basically. I mean, we can discuss the conceptual status of that later. But
I mean,
you,
if it's
you understand the concept of using density matrix.
so initially you have density matrix and then you have final.
yeah. Okay, so this is from Introductory Quantum Mechanics. I'm sorry.
Yeah, sorry.
So we can generalize this concept of measurement and introduce something called positive operator valued measure, where we have a set of positive operators, En, a sum of two identity, and the probability corresponding to the outcome n, and I think it's taking some time to. Yeah. So the nth outcome of this generalized measurement is has a probability given by this trace of rho En, and if you can decompose this En as some in terms of other operators mn dagger mn, then your final state after, if you have the nth outcome, is given by this state update rule mn rho mn dagger with some normalization. So these mn's are called cross operators, and yeah, so and you can, if you put mn to be the projection operators, then you get back the introductory quantum mechanics von Neumann measurement scheme, basically. So this is a more generalized setup, and you can realize it in through this scheme. Yeah. So you basically at the beginning you have a system and you have a measuring device or meter. You interact them for some time, capital T, and then you perform a projective measurement on the meter. And this is equivalent to updating the state of the system in terms of using the cross operators that I just had shown. So while talking about this cross operators, sorry, I was talking about POVM, the weak measurements are like specific class of POVMs. So we do not always want to project our system of interest to an eigenstate of an observable. So what we do is to perform weak measurements, which perturb the idea behind weak measurements is you perturb the system a little bit, and you also gain only a small amount of information in the process. So to give an example, suppose we have this phonon or photon number operator, and we know that these projectors are project into this Fock states n prime. But if you consider this cross operator defined as a sum over weighted sum of all these projectors, then you can see that this cross operator is not exactly projecting to one n prime, but it is like it is like leading to a weighted sum across all the different Fock states, and the weights are, for this example, I have chosen to be Gaussian around the project around n prime, and the value of kappa determines the strength of the measure. So, for example, if you choose kappa very small, then this operators, cross operators are identity, and you basically are not performing any measurements. But if you choose a very large kappa, then it leads to a projector to the state n prime. So in our discussion, we will assume that we are dealing with cross operators which have these Gaussian forms, and we will assume weak measurements, meaning that this kappa or corresponding parameter has a value which is much smaller than 1.
So, I don't know if you want that I will interrupt or
You can ask questions.
Sure, if you need to clarify.
so you have your system, and now you say that the system is you measure the number of phonons.
Yeah, I mean that was just an example to give an
Your
idea.
Kraus operators. I'm not. What's weak measurement? I understand. So you have a system that has some number of phonons, some quantum state.
Okay, yeah.
And now you can measure exactly what is the number, or you can make a weak measurement when you have a Gaussian distribution from the beginning, which slightly shifts.
Yeah.
So if this is Kraus story, it's this weak measurement, or it's something different?
Sorry.
It's the same. It's the same in the sense that if you do what you're saying, if you interact with the pointer in the way that you say, and then you look, okay, what would the effect, if I just want to describe this in terms of operators of the system, what's happening to the system, then you would use this kind of Kraus operator. So that scheme that you're talking about is one way of implementing this particular Kraus operator measurement scheme.
Question.
If you have eigenspace, let's say 5.
Fox at 5. Okay.
And then you apply this.
Yeah.
And let's say your kappa is pretty small.
Okay.
So then it will be all shifted from this operator to n plus 5.
Yeah. I mean,
this on the right, it's not operator. Oh, it's okay, it's operator. So if I understand, the initial state, if I understand, your initial state, it's some of the component time. What is your pointer is also discrete, or what is your point?
Pointer here in this case, I'm assuming it is discrete, but it
discrete. So and the initial state is
so
it's the initial coherent state with what alpha is.
Yeah, I mean, yeah, initial state could be alpha. Yeah, so I'm assuming so. Depending on
n,
how.
n prime. What is the sum of n?
Yeah, this is sum over n surrounding index.
Right, I notice Andrew has his mic open. Did you want to say something here, Andrew?
I was just going to comment at this point, the initial state of the system is anything, right? The point is you specify the Kraus operator that's telling you the kind of measurement you're doing on the system. The system state can be anything at this point. He just specified that whatever meter you use, this is the effect of that meter, right? So it has a discrete set of outcomes in prime, I think is the point.
the final outcome is one number, or what the reading is, or it's reading on the particular
So
projection
final,
on the state.
yeah, so final outcome is the reading you get at the meter.
The number.
Yeah, so but if the reading corresponds to one particular number or not, depends on the strength of your measurement. So if, for example, for weak measurements, you won't be able to tell from the reading of the pointer whether.
The initial state you have your pointer, which is a Gaussian, and maybe for weak measurement, it's very wide Gaussian.
Okay, yeah.
Shallow Gaussian. And then in the end, you get the number. And the number which you get, it's what is your reading? N prime?
Number, yeah, so for this outcome, you get the number.
Outcome is N prime.
Yeah, like the N prime outcome in general, but in this case, it's N prime.
Okay.
So quick measurements. Yes, so now that we have introduced weak measurements, we are ready to talk about weak continuous measurements. So the need for weak continuous measurements arise because in realistic situations, measurements have always noises. So if you want to have a finite signal to noise ratio, you'll need to perform the measurement. It cannot be instantaneous. You need to perform it over some time interval. And also during this, you might also wonder that during the course of your measurement, the state of the system might evolve. So that is also something you need to take into consideration. Also, apart from all this, you might want to do a real-time tracking of the system without perturbing it a lot. So this is where the concept of weak continuous measurement is coming. So it's basically you perform sequence of weak measurements in small time intervals. And so
just there is one long time. This time you break to some period, so there is a measurement, there is nothing.
No, so I assume that this all are, so between two consecutive, so I'm performing consecutive measurements and each are taking d tau time or small time d tau.
So the measurement is all the time, it just but you have particular moment when you make
yeah, so
fix it every time a new device. So if you can.
Yeah, so it's like so I talked about the POV and 0 to capital T time of time from when you're starting the interaction to making a projection. So you can think of it as like in d tau time interval, you're performing all the tasks and you're performing another set of measurements in the next time interval.
The full time is T. Then you make a large number of
segments. Yeah.
And there are some free between the measurements. There are some empty time.
No. There's no empty time.
But it's still discrete because you perform number. So
there is an empty time because you have to apply the Kraus operators with a time gap between them.
I don't know.
But he's going to take the continuum limit where that comes to when it comes to 0 and it truly becomes continuous. Okay, so the way you model this is you implement a Kraus operator every delta t, you implement the measurement every delta t, and then later on is going to take a limit as delta t goes to 0. So
you'll have infinite number of infinite information in there.
no, because you also, well, you'll see how he does it because you're not going to take just a limit whilst keeping the strength parameter the same. You're going to take a limit in such a way that the rate of information acquisition is constant. Let him proceed and you'll see how it goes.
Okay, so let's take the example of this Kraus operator, and we perform weak continuous measurements. So we assume that we apply these measurements in theta intervals, and here the strength of the measurement parameter kappa, we assume it to be proportional to the time interval we are doing the measurement in, and there's something there. Okay, so because you perform this sequential measurements, you get a sequence of readouts, and you can update your quantum state conditions on those readouts. And what you have at the end is basically a sequence of readouts and sequence of intermediate states, which is called a quantum trajectory. So you realize a quantum trajectory in this way through weak continuous measurements. And this is nothing, but this is not a abstract mathematical concept only. It's like this similar ideas have been applied in experiments as well. So this work by Berlin et al., where they do sequential measurements using a two-level atom and measure the and they progressively collapse the field of a cavity to a Fock state. And also this another example is, so they basically observe quantum trajectory in this experiment.
They perform all this measurement that they can calculate the quantum state. Say that they observe it.
So this is another experiment by Merge et al. In 2013, where they observe quantum trajectories of a superconducting transmon qubit, which is dispersively coupled to a cavity. And also for continuous variable systems, this experiment by Rossi et al., they observed the quantum trajectory of a continuously monitored macroscopic mechanical resonator.
So here's even two words. So observing and verifying.
Yeah.
So I understand you start your system, you make your coupling, you get this reading, and then you can calculate your quantum state. Now you have another system which will measure this quantum state. This is verifying.
So I'm not sure about this particular publication, but this previous one, what they do is like they also verify the quantum trajectories and they perform tomography on the quantum.
Usually, if I understand correctly, the tomography is only there. They don't check what's in between. They calculate, but this is kind of. Am I right?
Yeah, I think
you do your interaction, your state changes, which you can make calculation. You finish whatever, and then you say, is what you calculated is what your tomography tells you. Although the tomography really cannot do tomography because you have to, or maybe if you, I don't know how you can make tomography on one system, so you can have to repeat it. And then,
There's another, Andrew wants to make another comment.
Yeah, my comment here, Lev, is what they do in this
come here because you can
what they do in this experiment is they go part way through the quantum trajectory and they stop and look at all trajectories who predict the same state at that point. They do tomography on those set of states and they verify the prediction is correct. So you can stop at any point during the trajectory, and by comparing the results, you can verify the prediction of the trajectory is correct at that point.
So again, it's they stop in particular moment and they make one measurement. They don't repeat. It's not that they cannot make tomography on the one system.
Yeah. So Lev, what they do is they take a set of measurement. They do measurements many times. They look at the trajectories that predict the same state at that time. Then they compare the tomographic results on the subset of trajectories that has the same prediction. And then they can then verify that that is a correct state assignment.
So the ensemble is huge because it's very difficult to find something which will end up with the same state.
Lev, the ensemble is huge.
Yes. Okay.
Okay, let's carry on.
So now we are familiar with weak continuous measurements, and we will see where. So we can ask, how does the state of the system evolve, and what is the statistics of the measurement process? I'll talk about what I mean by that. And so this Chantasri-Dressel-Jordan stochastic path integral formalism comes into this place, and it characterizes the statistics of the measurement process. And we also get something, we can figure out what is the most likely path or the optimal path that the system is going to take during this continuous measurement. And this Chantasri-Dressel-Jordan formalism has been experimentally verified for continuously monitored transmon qubits, which is coupled to a waveguide by Weber et al. And this has been applied to study remote entanglement generation into transmon qubits. Another example is we also studied resonance, continuous monitoring of resonance from a resonance fluorescence from a superconducting qubit. And here they find multiple quantum caustics or multiple most likely paths. So, but this has not been, so far it had been limited to applications for qubits, but has not been applied to continuous variable systems. So in our work, we extend it to continuous variable systems. And to be specific, as I had already mentioned, continuously monitor quantum harmonic oscillator undergoing simultaneous continuous position momentum measurements. And because harmonic oscillators describe such a wide variety of systems from trapped atoms to mirrors, we are hopeful that we will see that this application of this formalism to our system will lead to results that are otherwise difficult to calculate for such systems. So now we have learned about weak continuous measurement, and with the CDJ formalism comes in, we can go on to describe our system. So we have a harmonic oscillator, which is coupled to two measuring devices, which are measuring its position and momentum simultaneously. And they are giving noisy readouts of this position momentum R1 and R2 in small d tau time interval. And as I had mentioned before, that this harmonic oscillator is in general Gaussian states. So I'll describe what I mean by that. So Gaussian states are defined as states with Wigner functions in Gaussian forms. So why do we choose Gaussian states? So first of all, it describes a wide variety of states like ground states, coherent states, squeeze states, thermal states. They're all Gaussian states. And also, apart from this, another unitary evolution and the measurement backaction for the Gaussian type cross operators we had just shown. The Gaussianity of the system is preserved. And another reason for this using Gaussian states is that only 5 parameters are sufficient to describe quantum state. So the first two are the expectation values of position and momentum, Q1, Q2, together as Q vector. I'll also call them quadratures. And also the covariance, 3 covariance matrix elements. So covariance matrix is noted as gamma, and this variance is of position momentum and covariance of position momentum. So for pure states, this determinant of this covariance matrix is 1. This is a necessary and sufficient condition. And for coherent states, this we have to remember that this covariance matrix is actually identical. So now that we know about the Gaussian states, we can talk about the evolution of our system. So there is unitary evolution due to this Hamiltonian x square plus p square, where we assume h bar is 1 and we take unit, mass, and frequency. So everything we will describe will be unitless. And there is also measurement backaction, the continuous measurements we are performing on the system. So and the measurement cross operators are, as I had said, that they are of Gaussian forms, we assume. And for readouts R1 and R2, they take these forms. And we can see that there are 2 parameters, tau1 and tau2. They are called collapse timescales, and they describe the inverse of the strength of the measurement. And as I had said before, we are considering weak measurements, which correspond to this time interval of measurement being much smaller than the collapse timescales. And there might be a question of measuring position and momentum simultaneously and also satisfying the uncertainty principle. So for this case, as we would expect, the uncertainty principle is satisfied. And mathematically, this is expressed as determinant of the covariance matrix being always greater than or equal to 1. So now in other cross operators, we can see how the state evolves. This evolves according to this equation, where we also have the unitary evolution and also the measurement back actions expressed in terms of cross operators. And this order of operation here does not matter if we only consider term still order d tau. So that is why we can write NP, MX dagger, NP dagger as well. And as I had mentioned before, this state of the system remains Gaussian under this evolution. And you can use this update equation to get the trajectories of this system. If you use this and get the evolution equations for the quadratures look like this. So let's dissect the equation a bit. So we have this omega matrix as 0, 1, minus 1, 0. B is a matrix dependent on the covariance matrix elements and the collapse tensor. It's called the diffusion matrix tensor. Diffusion tensor, and this R and X are scaled readouts and the scaled quadratures. So the first term here is, you can recognize it as the unitary evolution, as you would expect without any measurements. It's like differential equation of a harmonic oscillator. But the second one is what second one corresponds to measurement back action. And you can see that R minus X is the measurement record minus signal, which is the noise. It's characterizing the noise, and it is stochastic in nature. Therefore, we have a stochastic evolution of the quadratures here. And I will not go into the equations for the covariance matrix elements, but the important point is that the equations are deterministic and they are self-contained. So, which means that they don't store stochastic evolution, and the equations do not depend on the quadrature quadratures. And another point is, and we have proven it mathematically, that regardless of the initial state of the initial Gaussian state, the covariance matrix elements always go to steady state as time goes to infinity. And for equal measurement strength, which is tau 1 is tau 2, this at infinity, this covariance matrix goes to identity. So we basically observe the state purification under this continuous measurements, and for equal measurement strength, this purified state is a coherent state. And this, so here we show the evolution, sample evolution of the covariance matrix elements, just to give an idea of how they look. And you can see that the blue and green curves are the variances of position and momentum. Orange curve is the covariance of position and momentum. And you can see as time goes to infinity, the first two go to 1 and the covariance go to 0. So we're left with an identity matrix. And for simplicity, we will assume that our covariance matrix is identity to begin with. So, so our only state parameters that we should be state variables we should be worried about are the Q vectors, the quadratures. So now let's look at the how the quadratures evolve under this continuous measurement. So this is showing the evolution of quadratures. The left panel shows Q2 versus time. The bottom panel shows Q1 versus time, and the middle panel shows the trajectories in phase space. Here we start from an initial condition and simulate 5 sample trajectories. And from these two plots, you can see that the evolution is sinusoidal, but there is also stochasticity associated with them. And the plot in phase space shows spiral trajectories. So if you did not have any measurement backaction, it will lead to circular trajectories. But because there is measurement backaction, you see stochasticity and also spiraling of trajectory. And we will come back to this related to the energy, and we'll come back to it in a minute. So now that we know how the state of the system evolves, we ask where does the Chantasri-Dressel-Jordan formalism comes in. So what we have seen so far is we start from some state Qi, go to QM. This is just a schematic, and in time tau s, and we have data intervals during which the measurements are performed. And for the kth interval, we start from state Qk, we get readouts Rk and update the state to Qk plus 1. We're conditioned on the readouts, and we are left with a quantum trajectory. And if you look at the phase space from Qi to Qf, there will be many possible realizations depending on the intermediate set of readouts and intermediate set of states. So you take one of these realizations which correspond to a specific set of intermediate readouts and states, and you ask what is the probability density of realizing this particular trajectory. And this is, so Chantasri-Dressel-Jordan formalism tells us that you can get this probability density by performing this path integral with the exponential of the path integral on the exponential of a stochastic action. So this P is a variable conjugate to Q. It's not to be confused with the mechanical momentum. And so this basically is an action principle for continuous measurements. Now you can also ask, because you have the probability densities, I know how to calculate them. You can ask what is that one trajectory which extremizes the probability density, and it boils down to variational extremization of this stochastic action. We saw this in magenta in the schematic diagram, and this trajectories are called the most likely paths or optimal paths. So in summary, we have the probability densities to calculate as the path integrals over exponential of stochastic action. And the stochastic action can be written as time integrals of a stochastic Hamiltonian. Again, this not to be confused with the Hamiltonian of the system. And you can ask, so if you take delta S equal to 0, and you can express the equations for optimal paths in terms of the stochastic Hamiltonian. And this is basically the set of equations for optimal path that you will get. And you can see that the last two equations are same as the Hamilton equations. And for our particular system, this leads to this set of coupled differential equations. So you can see that P dot is, so the equations for P is basically a harmonic oscillator equation. But equation for Q has this unitary evolution, but there's also measurement backaction, which comes in the form of P, the conjugate momentum. And we will see that, so the mechanical energy for all practical purposes is basically Q1 square plus Q2 square. It's the norm of the quadrature vector. And if you start from a state Qy, Q1 and Q2y, to go to Q1 and Q2, then the mechanical energy as a function of time look like this, where this capital Q1 and capital Q2 correspond to the only unitary evolution of this system. And so the change in the mechanical energy depends on how far you are from the unitary evolution. And for the unitary evolution, you don't expect a change in energy. So the good news is the optimal paths can be solved for the system analytically, and the steady state of Covariance matrix element that we had already assumed. So this shows a sample optimal path for boundary condition chosen arbitrarily. And the first two show the evolution of the quadratures, and the last one shows the evolution of the expectation value of the mechanical energy.
You start with your system.
Yeah.
Then you have your measuring. And then you have this procedure that you make a limit of very small time and very weak.
Yeah.
And then, but it's not still, but what kind of, you said unitary evolution, but you have.
Unitary evolution is when you only consider the Hamiltonian and no measurement backaction. It's like only the simple harmonic oscillator evolution.
So, but the standard limit which you consider the interaction is strong enough, so it's not unitary.
Yeah, it is strong enough. Like we are performing weak measurements, but it's not identical to unitary. It has some sort of effect on the system. And the strength of the measurement determines that how pronounced the effect of the measurement backaction is. We will see this.
So then I think maybe the confusion is this is these things that are plotted here are the properties of the most likely path in the probability density. So obviously, in a real experiment, you get a stochastic path which is fluctuating. That's as this fluctuates around these numbers. That's what you would actually see.
If you go to limit, very small time and very small interaction. I think one can even ask if there is any. You have your system and then you make your coupling. And then you have this limit. But this limit still has kind of another parameter which tells how strong you some constraint, because you have some in addition to the limit, you have a constraint. strength, how strong your coupling altogether. Given the total strength, it's kind of, it's not that in the end you can take very, very weak coupling and nothing will happen. But this is not what they consider.
They're considering that basically the ratio. So earlier on, it was the parameter was proportional to dt, right? So the ratio of the parameter and dt remains constant as you take this limit. Okay, so if you change that parameter, you would see large. The larger that parameter is, the larger the stochastic jumps you're going to see in the trajectories.
But in the limit, the jumps remain the same. They do not become smaller.
No, they won't, because they depend on this parameter, which is the ratio of the measurement strength to dt, which is held fixed.
You have every simple interaction is extremely small. So I expect that the jump, I do not expect the jump. I said something is the limit. So if I make 10 measurements in between, each one will jump after each measurement. But if I make million one, which each one I describe, and the total strength is the same. So I do not expect still will have jumps.
But I'm not sure I understand. So the way I'm viewing it is like, is your individual measurements are weak, which leads to, which even if it leads to very small changes for us for one time state, over the time it will build up and you'll get spiral trajectories that I have shown. Is that?
No, these are not jumps, but you say, but you believe because of this interaction, your system will not be unitary, but it will start kind of, you're in a car, on a wet car, and you lose your track, and you kind of, this is not jumps. The word jumps is not appropriate, they're not jumps. It should be continuous.
Yeah, I mean,
jumps is when you make this
There
discrete measurement, there are
jumps.
jumps. If you don't make discrete measurement,
you get this stochastic trajectories because these are simulations.
this
So
is simulation. Now, if you make simulation, jumps, you'll make stems 10 times smaller, it will be smooth. Am I right?
Yes, this becomes a continuous process and the limit that dt goes to 0.
Wait, hang on a second, Andrew. I had it muted. If you want to make a comment now, go ahead.
Yeah, I was just saying you're right, Lev, that in the limit that dt goes to 0 and the strength goes to 0 at the same time, it becomes a continuous process. It's a noisy continuous process.
Okay, so, okay.
if you take very weak measurements,
It's not necessarily unitary. It doesn't mean that it's unitary, but it will be continuous. No jumps. Nothing like.
close to the
So it will be interesting. Can you perform maybe sometimes? Just it's interesting to see if you play with your. Of steps and with the delta tau, or I don't know how you call it, to see how.
yeah. So I actually had played with the parameters when I was performing simulation, and as you in each other on almost circular paths. And it should be, I'll talk about the probability densities of final state and it will be more quantitative.
But then again, you fix cells of the final.
For an optimal path, you'll need boundary conditions and you fix the final state.
It takes the simulation to reach up to the same point.
Yeah. So I will come to that. A sample optimal path, and you can see it in phase space as well. And as I said, that expectation value of mechanical energy, which is the distance from the origin. You start from an initial state, you will see that the energy is decreasing then increasing. We had performed simulations using the evolution equation of the quadrature, and also we have found Jordan conversion. And this plot basically shows the comparison between them. So the left panel is Q2. And you can see that the yellow line corresponds to the simulated and the dot dash curve corresponds to energy decrease in the system, and the optimal paths from the C-digit formalism. We can see that the analytical the results from the simulation, and also we will show a green sample trajectory just to show how the event for 3 separate times, tau equals to 2, tau equals to 3, tau equals to 5, and the probability densities of the and we can see that as time progresses, the states diffuse more. This probability density, and we will see this calculate the corresponding optimum path. And we can also calculate the momentum for these states where and we see that the energy conserving path corresponds to this momentum having 0. Evolution of the quadratures, and in other cases this is sinusoidal, as I had talked about before, and this mechanical paths, they either increase or decrease, and this is, although it looks straight line, it's actually a parabolic, but the slope is changing very slowly, so it's almost looks like and we can ask that of reaching one final state starting from an initial state. And this can be calculated by taking into account all possible intermediate and for our system, this can be, we have calculated it analytically. And for equal measurement strengths, tau is the distance of the final state from the unitary only. Probability, you can see that this is the global maximum. And if you look at the standard deviation of the probability density, which is measurements lead to more diffusion. So you'll see spreading out of the trajectories as goes as inversely inverse to tau. If you increase the strength, you'll see more diffusion around the probability density of the final state starting from an initial state. And the black wireframes are probability densities calculated from simulation. And you can see that they are matching very well. Do this contour plot on the phase space, where this dashed one so calculations corresponding to probability densities of these two values, and a solid one shows the corresponding contours for matching really well. And yeah, so to summarize, we have provided a stochastic variable system. And using this, you are able to completely characterize the statistics of the continuous measurements. And because of reaching a particular final state, we're hopeful that this analysis will be useful for feedback. So these are the references.
Okay, if there are people who have a hand or indicate in the chat room, we have only a couple of minutes, so I'm going to take Luke here first, and then let me know if
that's like the path, the optimal path. Is that different from the classical trajectory? The classical.
Yeah, I mean, so most likely pass. So in case of, if you only take the classical limit of the system where the circular trajectories, but in this case, I saw that there are like you can end up reaching different final state of different. I'm trying to find the plot for this. Yeah, but you won't see this trajectory in classical limit because in this case measurement is adding energy or withdrawing energy from the system.
Right. That's classically.
Yeah, it's
Any questions from Zoom? Okay.
Maybe stop sharing to see people.
I can see it. So in that case, I think we will conclude for now. Thanks everybody for coming. Please let me know if you're on Zoom. Please let me know how the Zoom experience was so that I can improve it for next week.
Matt, can I just take a minute before people log off?
Yes, go ahead, Andrew.
I just wanted to introduce a few people from my group that are here on the Zoom for the people that are Chapman folks. And so if you don't know me, I'm Andrew Jordan. I'm a new faculty member here. And so I know we've got Abhishek. I see who else is here? I think Erwin was here, Damalo. A few of my group members are also coming to these things as well. So just wanted to introduce them to you quickly. So maybe, we can do a longer introduction later. I just want to let you know these are people from my group that are joining from Rochester or from here as well.
Well, welcome everybody. Okay, thanks Andrew. So we'll see you all